In this short video, we're going to look at transitions between orbits in Niels Bohr's atomic model of the atom. So imagine we have two atomic orbitals, or two atomic orbits rather, and we have a lower energy level n equals 1 and an upper energy level n equals 2. And we're interested in a decay of the electron that's present in n equals 2 down to the n equals 1 level. Well, because of conservation of energy, if the electron decays, it's going to change its energy value. So it must liberate some energy as photons of light. So we saw in a previous video E equals h nu. Energy is Planck's constant h times by frequency nu. We want to calculate not only the energy E, but we want to calculate the color so that when I see the spectrum, I know exactly what the color represents. So the couple of equations you'll have to use is energy is minus the Rydberg constant, RH, multiplied by 1 over the final energy level squared minus 1 over the initial energy level squared. The other equation you're going to have to use is energy is hc over lambda. So we're going to use the n values to solve for E, and then we're going to plug in E here to solve for lambda. So let's see. So I know that energy is minus the Rydberg constant, which is negative 2.18 by 10 to the negative 18 joules. The final n is n equals 1. And actually, I don't want that. I want 2 and 3. I could have calculated 2 and 1, but I really wanted 3 and 2. So let's say my final value is 2. So I've got 1 over 2 squared. My initial value is 3, so I've got 1 over 3 squared. So I've got a number multiplied by a constant number of joules. So this should give me negative 3.03 by 10 to the negative 19 joules. Now, although this is a negative number, it's a positive energy because there's no such thing as negative energy. The negative here just means release, or the energy is exiting the system. It's being lost by the system, so this is a loss of a positive amount of energy. If we then use our equation here, we're actually going to cross multiply so that wavelength is hc over E. So the wavelength is hc over the energy. When we put the energy in, we take the absolute value of the energy. H is Planck's constant. This is a constant that you would learn. It's a very small constant, 6.63 by 10 to the negative 34 joule seconds. The speed of light, c, is a constant that you would learn. .00 by 10 to the 8 meter per second. And energy is our value from here. We're going to take the absolute energy. So 3.03 by 10 to the negative 19 joule. You can see that our units cancel out nicely. So joule cancels. We have a second here and a reciprocal second over here. So the only unit that survives is meter. So we're going to have wavelength in meter. Okay, so if we calculate this, this is wavelength is 6.56 by 10 to the negative 7 meter. If we convert this to nanometer, our meters cancel. Most times you report this value in nanometer because the unit is appropriate for the size of the number. Well, this gives us 657 nanometer, which is a band of red light. So we've accounted for red light production from the decay of an electron from the third orbital to the second orbital. So this was a 3-to-2 decay. Let's have a look at a 4-to-2 decay. So we're going a bit higher up in the layers of the atom now, but we're decaying down to the same position, the second level. So here energy is minus 2.18 by 10 to the negative 18 joules. So that's our Rydberg constant. We've got 1 over the final value. The final value here is 2, so 2 squared, minus 1 over 4 squared. And if we compute this, we get a value of negative 4.09 by 10 to the negative 19 joules. We now do the same process here. We solve for the wavelength. The wavelength is Planck's constant, 6.63 by 10 to the negative 34 joule seconds. The speed of light, because we're looking at light and it always travels at the same speed, 3 by 10 to the 8 meters per second, divided by the absolute value of our energy. So 4.09 by 10 to the negative 19 joules. Joule cancels, second cancels, and we have wavelength in meters, which is 4.86 by 10 to the negative 7 meters. We can convert this to nanometers again. This would, so we multiply by 10 to the 9. This would give us 486 nanometers, which is actually, what color light is that? That is going to be blue light. So I'm actually looking at page 92 in the Revell book. So there's a table there that would give you these values. These calculations just enforce where the numbers come from. So which is higher energy? Well, recall from a previous video, we said that importantly, the important relations are energy is proportional to frequency, which is proportional to 1 over wavelength. Well, we just calculated wavelength, and our red light had a longer wavelength because 657 is a greater number than 486. So this is our longer wavelength red light. So 1 over a larger number gives you a lower energy. So this is low energy or lower energy, whereas our blue light is higher energy. This is one reason why, so maybe a dated but still a practical application. People that develop or expose their own film, photographic film, they use a red light room because the red light has a low energy and it won't develop the film. This is also why there's a push now to minimize the amount of blue light that people are exposed to when they use a computer screen, or the last time you went to have your eyes checked. The optician probably suggested a test for blue light exposure. It's because blue light is high energy, and over time it can damage your eyes.